So after the astronauts get back from the space station, it usually takes them a while to get adjusted to life on Earth. With the whole gravity thing,
Our understanding of space and time has grown a lot, but there's still so much we don't know. How do black holes work? Is time travel real? Could wormholes let us take shortcuts through the universe? We can't fully answer those questions, but we can explore them based on current scientific theories. Today, we'll try to understand these mysteries and picture the invisible fabric of the cosmos. Imagine space-time as a giant imaginary grid spread across the universe. It's not just sitting there. It changes and reacts to everything around it. We've had some wrong ideas about space-time, which has led to misunderstandings about how the universe works. But by rethinking these ideas, we can start to see space-time differently, and that could completely change how we see the universe. So, what if space isn't just empty? Imagine the empty space between stars and planets is actually an invisible fabric that bends and warps. This invisible force shapes the universe, and it's happening all around us. This is where gravity, the great cosmic force, comes into play. Gravity isn't just a force that pulls objects together. It's the main thing that shapes the space-time fabric. Big objects like stars and planets don't just float in space. They actually curve the space around them. To picture this, think about dropping a heavy ball on a stretched-out rubber sheet. The ball would make the sheet dip, and if you roll smaller balls around it, they would fall towards the dip. The sun does something similar. It makes space-time curve, and planets like Earth follow that curve, staying in orbit around the sun. This isn't just true for big things like stars. Even on a smaller scale, Earth's gravity holds the moon and satellites in orbit in the same way. Space-time curvature works at all levels. A good example of space-time being flexible is tides. The moon's gravity pulls on Earth, causing the oceans to rise and fall. That's space-time in action, showing how one object can affect something far away. But space-time is influenced by more than just things we can see. There's also dark matter, a mysterious substance that doesn't emit light but still affects gravity. Dark matter helps shape space-time too, influencing galaxies and the structure of the universe, even though we can't see it. The sun, for instance, creates a gravitational well in space-time. Objects like planets, asteroids, and comets fall into this well, making them orbit the sun. This shows that even in what seems like empty space, gravity is always at work, shaping the movement of objects. Gravity also creates a network of forces between planets, moons, and other objects, constantly affecting how everything moves in our solar system and beyond. Now, what if something was so massive that it tore a hole in space-time? This is the reality of black holes, where gravity becomes so strong that not even light can escape. Black holes are the most extreme example of space-time warping. They create a point called the event horizon, where the rules of physics seem to break down. While black holes represent one of the most extreme examples of space-time distortion, they also provide insight into how space-time behaves under extreme conditions. The study of black holes isn't just about understanding what happens inside these mysterious objects. It's about pushing the limits of our knowledge of gravity and physics. Black holes challenge our understanding of quantum mechanics, and they may even hold the key to unifying quantum physics with general relativity. As black holes collide and merge, the gravitational waves they emit allow scientists to study phenomena that can't be observed through traditional telescopes. By analyzing these waves, we can learn more about the mass and spin of black holes, as well as the processes involved in their formation. This research helps us understand not just black holes, but the universe's evolution itself. Gravitational wave astronomy is still a young field, but its potential is enormous. With better detection technology, we may one day even be able to map the invisible ripples of the cosmos, offering a new way to explore the universe's history and future. As you get close to a black hole, space-time stretches and speeds up. This can lead to spaghettification, where objects get stretched into long, thin strands, just like spaghetti, by the black hole's intense gravity. When two black holes collide, they create powerful ripples in space-time called gravitational waves. These waves were first predicted by Einstein and finally detected in 2015. Gravitational waves travel across the universe, carrying information about violent events, and when they pass through Earth, they shake the planet ever so slightly. These waves come from black holes merging, and studying them has opened up a whole new way to observe the universe. Scientists can now study events that were invisible before, like the merging of black holes and neutron stars. Gravitational waves have revealed how flexible space-time is, but what if we could manipulate space-time for things like time travel? Time travel has long been part of science fiction, but it's possible in theory. For instance, there's the grandfather paradox. If you went back in time and prevented your grandparents from meeting, would you even exist? Some physicists have tried to solve this with ideas like the self-consistency theory, which says that even if you travel to the past, you can't change it. Another idea is that time travel might create new timelines, leaving the original unchanged. While time travel might remain theoretical, wormholes are another intriguing idea. These are tunnels through space-time that could connect distant parts of the universe. In theory, they might allow for shortcuts in both space and time. But to stay open, wormholes would need exotic matter, which we haven't yet found. Wormholes and time travel are possible according to the math, but we haven't found a way to make them real. These ideas push the limits of what we know and drive ongoing research. Space-time is more than just a backdrop. It's a flexible, interactive fabric. By understanding this, we can explore exciting new ideas about the universe. This could lead to new technologies and change how we think about space, time, and our role in the cosmos.